All right, so I just want to go over real quick. Please put away your quizzes. I know that you're looking over them. The answer key is posted on Blackboard. You generally did pretty well. This is in line with the, I know it doesn't feel that way when you look at it. Like, oh my gosh, I know nothing, I learned nothing. It's reps. So think of it this way. Quizzes can be intimidating, but it's 1/4 of 10% of your final grade. But remember that you get half of that for attendance. So basically 5% of your final grade is you show up and you get 5% of it. And then the other 5% is getting that mid-full rep. Now the reason why that's good is because now you know, you have a general idea of how I'm going to ask questions on the exam, right? And so work on it, you work on those problems, and then by the time you get on the exam, which is 20% of your final grade, you do a lot better, typically. And so what ended up happening is the class median, I believe, was a 72. That's typically in line with past semesters. And then the exam median is typically around 88 to 90. And it is very common. This happens every semester, and I anticipate it will happen this semester. Student comes in, they take the quiz, they get 50 points extra credit, and then get about 4 points of what they put on the quiz, right? I've seen many students who've done that on quiz 1 turn around and get an A on the first exam. That's very common. So don't feel panicked. It's a repetition. You now know better about how we're going to ask questions on the exam.
Okay. Also, I want to quickly go over my policy. If there's any misgrades, I have a policy you have to wait 24 hours. Have I told you the story about my student who followed me home? It was a final exam. If she had gotten the 5, it didn't matter to her final grade. She could have just let it go. She would have had an A in the class no matter what. It was not worth it. But the cops thought it was a problem. So it's an opportunity. There's a shell shock if you're like, oh my gosh, I thought I did a lot better than this. Take a day, breathe. If I graded it wrong today, it will still be graded wrong tomorrow. If I added up your score wrong today, I still have added it wrong tomorrow. It's fine. Just let it go for a day. All right? Fair. All right. So in section 2, we went over arithmetic logic units. So what we're doing is we're slowly building up the advanced digital system. So in section 2, you learned about adders and subtractors, and we discussed that quote from Hobbes about how multiplication and division is just a set of additions and subtractions. And we discussed several algorithms on how to do addition, subtraction, multiplication, and division. In the case of, if you want to exceed that 2 to the 32 minus 1 value, you have to use floating point arithmetic. So you learned about the IEEE 754 format. You have your sign bit, your exponent. You learn how to calculate those, and then how do you do the mantissa and perform those additions and subtractions. And then you learn about sign multiplication. We did 2 examples of that where you have, we did 8 times -9 or -8 times 9. How do you do the multiplier and multiplicand? And then you learn 2 different algorithms for performing division, restoring and non-restoring, and you're able to differentiate how to do positive and the trade-offs in area and performance. And you saw an example of that in the actual algorithm. So now we're going to move to how, so you performed all of these certain operations in the ALU. Well, now how do you store them? How do you store them efficiently, and how do you do it to actually make the computer run fast? So this section is called Large and Fast Memory Hierarchy. In the textbook, it's chapter 5. I'm going in a different order because I find if you build up the, you teach about the ALU and then you teach the memory and then you put it all together in the data path, which is in chapter 4, it asks students actually demonstrate a better understanding because they learn all the different forms of memory addressing, which we'll go over in this section. And so if you recall, when I was going off about what MIPS is, and I have this the original paper posted on Blackboard, I was talking about how you actually store memory. So this was from a topical guide objective in section 1. So you have this repeated uses of register in a basic block of code, prevents redundant load and store. So I did this whole thing where I was dancing around where you're this local memory and you're the long-term memory. So in this section, we're actually going to learn how that's done in the MIPS data path. So topical object 3.1 is memory versus registers. So registers are these local 32-bit values that are constantly updated, and they're non-volatile. I mean, they're volatile, meaning if the computer turns off, you have to store them really quickly, but it can't store information without a constant refreshing from the clock signal. Whereas if the non-volatile memory, you actually can store it when the computer turns off. So that's where we'll learn about that and how that's regulated by the operating system. So memory versus registers in MIPS. So access to registers is faster. And the reason why it's specifically designed to be fast is that we can get it quickly, perform some operation in the arithmetic logic unit, and then store it back in the register. So you want it done fastly. Yes?
When we say memory here, are we referring to system memory, or would that include cache memory?
It includes cache memory. Yeah. So registers are local copies, and then we're going to learn later on in this section about the difference between cache and like read-only memory and system memory. It's a good question. So arithmetic operations in MIPS must use registers, not memory. So this is going to be important when especially when we get into transferring some basic C code into MIPS. You don't want to use load and store unless you absolutely have to. And that's when you're going to do array operations or storing everything after you complete the function. And the reason why you must use it is because it's faster. And MIPS has 32 registers. Now in the MIPS screen sheet on Blackboard, we'll be going over this on an exam where I require you to do that. I will provide the MIPS screen sheet. But there are 32 registers. We have 8 what are known as saved registers, where these are actually where you store variables. So if I equals j plus k, you write that out in C. There's a specific saved register for I, there's a specific saved register for j, and there's a specific saved register for k. Now, if you're doing I equals j plus k plus L, in the MIPS, the arithmetic logic unit discussed last section, we have 2 inputs, right? So I can't add 3 values. So what I'm doing is I'm going to perform an addition and store what's known as a temporary register. So you have I equals j plus k plus L. You can't put j plus k equals I, because that's not what the coder asked for, right? I equals j plus k plus L. So you can't put j plus k in there. So you take that result and store it in a temporary register, and you do temporary register plus L, and that value is going to be equal to I. So that's how you actually use it to make sure that you're actually doing what the coder writes. So as a result, results in fewer pipelining delays. Now we haven't really talked much about the concept of pipelining, but I have discussed this idea that there's 5 stages, and first you're going to learn these known as the single cycle data path. And that's where everything is done in one cycle. It's a longer cycle, but you do the instruction fetch, the decode, the execution, the memory, and then the write back, all in one cycle. But if you have pipelining, you're actually putting buffers between each stage. And you can actually have faster clock cycles, and then you move the instruction to the next stage, and then you can actually put in the second instruction. So you're significantly improving the throughput of the exact same device. Now, there's trade-offs to that. It requires a lot of overhead and a lot of what's known as hazard detection, and we'll go all over that in section 6. So registers are dual read, single write SRAM, and memory is single read, single write DRAM. So let me ask you a question: why do you think we might have to make registers as dual read? Dual read means that I can read it twice at the same time. Yeah, that's a pretty good guess. So let's say I'm performing some sort of operation where I need the same variable twice. For some reason, the coder has written j equals I plus I. Well, I need to grab that value twice and perform the operation and store that result in j. So the R-type instructions are you can grab 2 values from registers, perform some operation on them, and store them in another register. Well, what if those 2 values I need happen to be the exact same register? I have to read it twice. That's why we've designed registers as dual read, single write SRAM. And memory, if I'm loading and storing, I only need to do it once. So that's why we do it as single read, single write. And did you all do DRAM and SRAM in 235? No? Okay, I'm getting a lot of no's there. So basically the whole idea is it's static random access memory and dynamic random access memory. So dynamic, it's meant to be very fast, but you're constantly refreshing. DRAM is actually smaller. So this is what we're using in cache, like you were asking. A lot of cache memory uses DRAM. So it's constantly refreshing. And SRAM is going to be larger, but the reason you're using larger and it's slightly smaller in the registers is to be able to perform that dual read, single write, and it holds those specific value and is faster to overwrite. So this DRAM, it allows us, if we need to do one and then get out of there, that's the best. But if we need to be able to perform operations on it pretty quickly, we only use the static random access memory. Yeah.
So in typical computer systems, is static RAM only used for registers?
Typically, yes. Any other questions? I know I kind of just randomly threw out a pretty complex memory concept on you. If you want, it's more of a lower level stuff, something I would go over in CMOS VLSI design, precisely how to design that. But for now, what you need to know is that registers, you need to be able to read them twice, but you can only write to it once. You cannot write to it twice at the same time. That's an example of a hazard. Like I talked about hazard detection. One hazard is what happens if you're having two instructions try to write to the same register at the same time. So we don't allow that. We specifically do not permit that in the design. And we'll go over to how we'll discuss exactly how that's done when we've designed the full data path. So this is the concept, this idea of byte addressing, I have found is typically one of the more confusing concepts to students. It's the reason why I make this, in fact, the specific reason why I initially chose to do topical byte objectives is because I found students just were really struggling with this concept of byte addressing. It's actually really simple when you break it down, but you have to break it down. So byte addressing means that the index points to a byte, or 8 bits, of memory. Now, what does this mean? Now, in MIPS, we have 32 bits. Now, you can have in your non-volatile memory, you can store it as a word, or a half word, or a byte. So if you're doing an 8-bit computer architecture, like you're using an 8-bit architecture to do Super Nintendo, for example, you want to be able to access an 8-bit value and get that 8 bits out of memory. You actually, instead of having larger chunks of memory, you can have it in smaller consecutive chunks. So which means that if I need 32 bits, and I'm using a byte addressed machine in memory, what that means is I point to the first chunk and say, I want this first 8, and then the computer will give me the next 3. So that gives me the 32 bits. Now, I don't want to go too much into, how many of you have taken an operating systems course, like in computer science? Okay, so you're familiar, okay, so D, you're familiar with it. What's the term thrashing? Are you familiar with the word thrashing? Okay, so the idea of thrashing is what happens when the computer is performing more load store operations than actual arithmetic operations. You're switching back and forth between memory more than your computer is actually doing something. And you get familiar with that. You ever have your computer run extremely slow, and you turn your computer on and it turns back on and it's running fine? Well, the reason why is because when the operating system is assigning where all these memory elements are, there's a number of different algorithms where it tries to actually, least recently used, most recently used, where it's trying to say, okay, I need to replace this in memory, and then I have to point to it. And so every pointer requires another memory element. And so what ends up happening is when you write code, you have to actually delete your pointers. Now, Java does that for you. That's garbage. You'll remember garbage collection in Java classes that you've taken. Java is actually going through and saying, all right, we'll reallocate the memory for you. But it has a little bit of overhead, which is why Java tends to run a little slower. But it's simpler to code. If you're coding in C or C++, and you say, I want my first row is where I'm going to store my array. So somebody has to be here. Darren's my first member of the byte addressing here. So I'm pointing at Darren, and I need a memory element here that's constantly saying this is my array, right? And so I go in there, here I say I want 32 bits, so I say I need, the instruction says I need Darren, and what is known by the architecture is like, okay, I need Darren, then Alexis, then me, and then Kate. So they're my 32 bits. So it does that intuitively. But sometimes I'm like, okay, well, I need to figure out, I don't want to just use the full 2 rows. I need to space the computer out. So sometimes the operating system says, all right, well, I'm going to take Kate, I'm going to move Kate in the back because that's not being used very much. And so let's try to space it out so that way it can find everything as fast as possible. So there's not a guarantee that it's going to be together in the operating system. But I don't want to go into too much because that's like weeks of lecture in operating systems. But for now, what you need to know is that MIPS, if I, let's say I do a load instruction, right? So it's going to be a load word. And here's S1, so that's, remember that notation? And then I have 8 S3. So that's the notation for load word. Here's what this means. This means that, remember I was pointing at Darren? The value that I have that says where Darren is the value of S3, right? And so I need an offset. I would be going 8 elements down. So since it's 8 bits, I don't want to just go next to Alexis. I would have to go 8 elements down. So I'm actually multiplying it by 4 because 4 times A is 32. So I'm going to my next element, right? Now I'm all the way down track. We'll go into what all that means. But this is the way is how you actually separate the memory out. And here, when we start getting into 3.3, that'll become more clear. So 3.3 goes all the way through pseudo direct. So 3.3, you will see this problem in the future. So there's 5 types of memory addressing. So 3.3 will be state and define the 5 types of memory addressing and describe each using an example drawing. So when you see this question on the exam, you need to state the 5, you need to define them with a word, and then you need to draw it out. So immediate, the operand is constant within the instruction itself. So here's what that means. So if I have an instruction where I have I equals j plus 5, for example, right? So RS is going to be j. RT is going to be I. That means I'm going to take 5-bit value there. I'm going to get a 32-bit value, and we'll discuss that when we get to base addressing. But then I'm actually storing the value 5 in this immediate value, which means that that 16-bit value can actually hold a number. So in this case, immediate addressing is just saying that I can actually store a constant in the instruction itself. So that's a form of memory, and that's known as immediate addressing. So what happens is when you write your code, you have your compiler, compiles it down to machine language, you have a compiler-driven encoding in the micro engine, the value 5 will actually be stored in the instruction memory. So next, we go to register addressing, and this is kind of starting to get into what it was that I'm alluding to. So we have this value RS. So it's 5 bits because we have 32 registers, and 2 to the 5 is 32. So RS tells me which register contains the value that I want. So if you remember earlier, I talked about how S1 refers to the 16th register plus. So S0 is the saved register, so it's 16. S1 becomes 17. So what ends up happening is, so I have 16 and 17, right? What ends up happening here is that the 5 bits come in, go to a 5 to 32-bit decoder here, and what ends up happening is this goes in, and it comes out, and it's like 0, 0, 0, 0, goes all the way. The 17th value is 1. And then all the rest of them are zeros. And then they go to these SRAMs. So I want a dual read, single write. So what ends up happening is this one goes to one of the write values in the SRAM. It says to one of the read values in the SRAM, puts the value on the output, and then you get your 32-bit result. So if the other one is S3, so that becomes it goes the same thing, goes all the way. So it's 1 here and a bunch of zeros. So it goes to the next set of registers. It reads this one on the output and reads that one on the output. So it goes to the register through the 5 to 32-bit decoder, indicates specifically which one I want, and then puts the value on the output. And that's known as register addressing. So it's a 5 to 32-bit decoder. The address is here. It's converted. It goes straight there. And a good analogy I can use is if you think about sending a letter to an address. You know it's like 8120, right? So you know somehow that I need to get to a specific road, and I need to get to a specific house. So from there, what I'm doing is I'm converting that value, and let's say the house is 8,000, right? And you know that the homes go in units of 1,000. So there's 1,000, 2,000, 3,000. You're not looking for the 8,000th house, right? You have to look for a very specific element in that house. So like 1,000, 2,000, 3,000. You know that. That's your form of addressing. So the byte addressing in MIPS goes by units of 8 when we get to this data memory. But here, I have 32 of them. I know it has to be one of these 32. The register instruction tells me which value I need to get to. I convert it, so I have 32 values. There's only one that's 1. It goes to that value and then reads it. Or in the case of if this is RD, it goes to that value, converts it, and sends the value there for a write. When we get to the data path design, you'll see how it's differentiated. So base addressing. So this is where we start getting into dealing with data memory. So here we are dealing with the registers, and data memory is your separate element where you do load and stores. And so what's happening here is I need to calculate the address and specifically which address I want, right? So in this case, I have a value RS. So RS is from that, I keep pointing at Darren, but this is a good example. So that value that points to where Darren's location is, I'm pointing, I say I need to go to chair 1, right? So I am 1. And then there's some sort of conversion where the converter points to every single one of you, and the only valid value is going here. Does that make sense? So here I know the value is 1. It can be 1 of 32, and I have 1 point. So I know it's not you. I know it's not you. I know it's not you, right? From there, it gets the value from the register of where I need to go and puts it towards the arithmetic logic unit. Now, at the same time, let's say I have an offset. So I have an offset of 2. So Darren is my initial array. And I have an offset of 2. That tells me that I need to go to the D. So what I do is the arithmetic ALU is saying initial value, add 2. So since it's 16 bits, and we need to put a 32-bit value into the arithmetic logic unit, we have here a notation that's a dash and it says 16. That indicates the 16-bit bus. And then we do a sign extension. So since it's a positive value, we just read the positive value, the most significant bit, and just extend that value. If it's all zeros, just make it zeros. If it's a 1, that means it's a negative number. Make it all 1, right? So that means it's a 32-bit value, which is why we have a 32-bit value in here. We take our initial value. They are sent to the arithmetic logic unit, and they are added. And then it goes to the data memory. So what that means is that tells this result of the addition in the arithmetic logic unit is the actual element in data memory that I want. And that's that first of the 4 that's in byte addressing. And so that's known as base addressing, meaning that the first element of an array is base. So if I'm going to a second element, right, my first element is going. Now let's say for some reason I have a negative number. So if I have a negative number in the immediate, it'll sign extend. It extends all 1s. So let's say I want to say negative 1, right? So Bowen is my base. I've subtracted 1. So now I'm over to Forest. See how that works? So it adds it up and it's pointing. And then Forest has some element or value that I need to continue the function. So that's how base addressing works. That's how I go from what's in the function to actually getting something in data memory. Same thing with storing. So this operation is used for both loading and storing. So either I want to get it or I want to store it back. So I'm adding the two values in Alexis and Kate, right? I perform that operation. I'm storing it here. Aaron gives me, and then I say, okay, I need to store it. So first I get the value, and then I have another value that's pointing to Bowen, who is my base address. So I get the value, say you're my base address, and then the immediate value I have to subtract 1. So basically what I'm doing is I'm taking the value that I've calculated here in my local register, and I'm storing them in data memory. And that's all done using base addressing. And so the next two types are known as PC relative and pseudo direct. So PC relative is the branch address. The branch address is the sum of the PC, which is program counter, and a constant in the instruction. So in this case, what PC relative is doing is say if I is equal to j, right? And then I have some sort of number of instructions. And then I have another instruction, Q++. So let's say the number of instructions here is 4. Right? So what that means is I want to go past 4. Let's say I does not equal j. So I have to go past those instructions, right? So that's known as a branch. So the branch address is this value. So we're here. Then when you get into the data path, when you run this portion here that I draw, every single time it needs to increment to the next instruction in order to go to the next instruction. So in this case, it adds 4. The reason we're adding 4 is because we're using byte addressing. So instead of going to one element, so I need, instead of saying Aaron has 32, Aaron only has 8. Right? So Aaron has 8, I add 1, 2, 3, 4. We put them together, we put the 4 bytes together, the 4 byte addresses, into one value, and that tells me where the next instruction is going to be. So the instruction memory is stored in values of bytes. So you need to add 4 every time. So what ends up happening is you have the I equals j, and then the data path naturally increments to the next instruction. So if there's 4 instructions in here, and we got to get down here, I need to add 4 to go past them. So that value that I'm adding a 4 is going to be stored in the immediate. So if the branch is met, you have to, the branch condition is met, then you have to branch past those elements. So that comparison is done in the arithmetic logic. I'll get to your quick question in a second. What ends up happening is I get the value 4, I sign extend it, and then I have this shift left 2. SL2 stands for shift left by 2. So let's say I have 4 here, right? And it's a bunch of zeros. I have to shift left by 2. So that becomes 1, 0, 0, 0, 0. So shifting left by 2 is the same thing as multiplying by 4. And the reason we do that, again, is because of byte addressing. So if I need whatever, like here, I know that I can go, I'm going to increment by 1, right? So here I increment by 1. This is the same thing as 1 times 4. If I need to branch 4 instructions using byte addressing, each one contains 4 bytes, right? So if I have 4 instructions, I need to do 16. If I have to do 5, I need to do 20. If I have to do 8, I need to do 32. The easiest way to do that without having to send it to an arithmetic logic unit, you don't have to multiply by 4 because you don't have to go through that sign multiplication that you learned last class, right? The easiest way to do it is just shift left by 2. So I need to go, let's say you want to branch to 4. That means I need to go 16 bytes to find the instruction that I want to execute. Does that make sense? So that's why I shift left here. Now, Then we take that value. So if I want to branch 4, I sign extend it. I multiply it by 4. It is now 16. Then I have the next instruction. When I add these values, that'll be the instruction that I need to go to next after the branch. And then finally, this goes to instruction memory. Now in a bit, I'm actually going to describe why it's important that we keep instruction memory and data memory separate. But in this case, that tells us precisely where we want to go. So if the branch is met, we just go there instead of doing all the instructions in the if statement. Kate, what's your question?
What's being added with the PC?
4.
Oh, okay.
Yeah, that is in quotes 4. So this is not the arithmetic logic unit. This is just a separate adder, which is why there's a plus sign here. But yeah, that for those of you, especially if you're watching this on the video later, it looks like that. It's just 4 in quotes. All right, so last but certainly not least is pseudo direct. It's a jump address. So think about it this way. You write a function. You go write code, you've written a main function, and then you have another function. So you perform some code in that function, and then you have to get back to the main function to perform the next operation, right? So you have to have some type of function that jumps back to that value. So that is known as pseudo-direct. Now the reason it's called pseudo-direct is because we don't have a 32-bit value that tells us what we need to do. We have to be clever and only use 26. So what we're doing in this case is a different type of instruction where the opcode is 6 bits, and then the other 26 bits are used to indicate the actual jump address. So first, since it's 26 bits, and we have to get to another address, and we're using byte addressing in MIPS, the first thing we have to do is multiply by 4. So we have a 26-bit value in. We shift left by 2, and then we have a 28-bit value on the output there. So we've multiplied by 2, and we now have 28 bits. So this is why this is called pseudo-direct, because we don't have the initial 32-bit value. So the next thing we do is we perform our PC plus 4. And when you write data path, you're going to see just this PC plus 4 notation. And then this value here, now this circle with a little line in here, this means concatenate. All right, how many of you are familiar with concatenation? Okay, a good number of you. You'll have to kind of do something with strings where you're taking elements. What's going on here is we need a 32-bit value to indicate what the instruction memory is, right? So what we are doing is we are taking the 4 most significant bits from PC plus 4, concatenating them to the jump address, and then sending it to the instruction memory. Yes? The 4 most significant bits, okay, so the 4 most significant bits of PC plus 4, so think of it this way. Remember I said yesterday in restoring and non-restoring division, that the most significant bit of the quotient becomes the least significant bit of the remainder, because that's the form of shifting. What you're doing is you're copying the 4 most significant bits of the PC plus 4, and they become the 4 most significant bits of the pseudo-direct jump address. So most significant bits to most significant bits. So the 4 most significant bits. So to review, the value is actually in the instruction. It's 26 bits. You shift left by 2 to multiply it by 4 to account for byte addressing. And then, so you still only have 28 bits. So what we do is we just copy the 4 most significant bits from PC plus 4, and we put them on in front. And we concatenate. So typically it's going to be, more than likely than not, it's going to be 0, 0, 0, 0, because if you think about it this way, if you have, if you're running your 2 to the 29th instruction, you're writing quite the big program. So more than likely you're not, definitely not in this class. I'm not asking you to write 2 to 29 lines of code. That's insane. I'd have to pay you. Someone's asking you to write that much code, tell them to pay you a lot of money. But then it goes back to instruction memory. because it's jumping. So basically it's saying, well, I've now calculated the jump address. So think about it this way. If you did instruction 16, that's what we need to get back to in main. So the instructions that you're actually writing in C or Java. And then you jump down to, you perform the operation of the function. Well, you need to get to instruction 17, right? So instruction 17, this is going to be 17 times 4, right? So that's going to be 68. So how do I get to 68? Well, I have the value 68 stored here. I actually have the value 17 stored here, sorry. Shift left by 2, now it's 68. I still need 4 bits. So that it was, it's going to be doing instructions 32 or whatever it is you actually, however many you have in your function. It's highly unlikely it's going to be 2 to the 29. So those 4 most significant bits are going to be 0, which means it's still 68. You go to the 17th instruction in main, and you continue on in main as you did before. So that's what the jump does for you. Does anybody have, before I move on, since I know that's a quiz/test question, it's an important one too. Does anybody have any questions about this? I know it can be a pretty complex, I know I just threw a major concept in. Yes?
What do op, RS, RT, and all those?
Okay, so we're going to be getting into instructions here in a bit. I know we'll get there sooner or later. Okay, so op is opcode. So there's 3 types. We'll get into instruction types in a bit. But what that means is RS, register, RT, and RD. So if you recall from ART, are 3 types of instructions we'll go over. R type, which is register type, I type is immediate type, and J type is jump. And so R type, this is an example of an I type instruction because we save the 16 bits for immediate. But the RS, RT, and RD are register addresses. So anything register addressing, what we're doing is it's 5 bits here, converting it to a 32-bit value using a 5 to 32 decoder, and it tells us which register it is. So opcode is the 6-bit value that tells us what type of instruction we're doing. So that's what this is, 6 bits. At this moment, you don't need to be able, you wouldn't need to write the number of bits on this particular problem for successful answering on the. What you need to do is you'd have to write it out and indicate that you would know that the actual instruction, when it's compiled, contains a value. So that's actually a form of memory addressing. Did that answer your question? Any other questions? All right. All right, so here I was alluding to this concept of separating out and byte addressing and you move them around. So the whole idea in memory is we want to use the memory as efficiently as possible. So there's 2 things that you need. So actually 3.4, let me do my little star trick again here. You're going to see this question again. This is actually very important no matter what you're doing in your career, this idea of the principle of locality. So the principle of locality is a program tends to access data that forms a physical cluster in memory. Multiple accesses may be made within the same block. Right, so I have these local registers that I'm constantly using. If I'm going to do something in a function, I'm going to use these registers over and over again until I perform the operations that I need. And then I'm going to want to switch them over to the non-volatile memory, right? And so there's 2 types of locality, temporal and spatial. So T, temporal, and S, spatial. So temporal is time, and spatial is space. So time means if I'm going to use some register, I'm more than likely going to use that register again very soon. So formally defined temporal locality, if an item is referenced, it will tend to be referenced again soon. In spatial locality, if an item is referenced, items whose memory addresses are close by it will tend to be referenced soon. For example, more than likely, if I have a function here that references Bowen, more than likely I'm going to reference them in Hebrew, right? More than likely because the fact that we're storing them all in the same area means that you're more than likely going to be in the same program. So the operating systems have to do that. They have to worry about keeping things close to one another, both in space and in time. So that means that you want to be using, this is just efficient coding. How many times have you written lots of code and you only use a variable once? You use a variable over and over again. That's an example of temporal locality. And in spatial localities, the best way to do it is using arrays or vectors, keeping everything close together. And so the operating system typically will try to keep everything close together. And how it will do that is by using efficient cache hierarchies. Meaning that I want to use certain elements of the computer at certain times, and I want to swap them out when I'm done in an efficient manner. And you don't want to do too much swapping, because otherwise you get that thrashing. So you want to swap them out in a way that still allows the computer to perform the task it's using in an efficient manner. So the whole idea is this idea of principal locality. And so memory hierarchy, I actually defined it here in 3.5, is a structure that uses multiple levels of memory in order to improve memory access time. And so level 1, so typically there are 3 levels of cache. And data and research has demonstrated that after you go past 3 levels of cache, you tend to lose efficiency. And we'll go over a couple of problems discussing something called average memory access time that shows that. But generally, you have a very fast level of cache, then you have a slightly larger but slightly slower level of cache, and then you have a slightly larger, slightly slower level of cache in level 3. And then you can actually go to different levels of cache before having gone to this very slow and non-volatile memory. And then you take the ones that you need to perform the operations on, and that's what you put in your registers. Does anybody have any questions on that? Right. So here's what I mean by, so this is kind of what I just described. This is a kind of a graphical description of it. So the processor, so you have like comparisons of speed, size, cost, and current technology. So you have your fastest type of memory, which are your registers. Registers are very fast and easy to access. They're small. But guess what? They cost a lot more. Like, why don't you just make the whole computer out of cache memory? Because you only have so much cache. So as the cost decreases, well, the size increases here, and the access time also decreases. So that's why you have 3 levels of cache memory. You want to be able to take advantage of the fact that it's fast, yet have a little bit of trade-off in order to reduce costs. So the memory hierarchy is a good example of designing an advanced usual system in a way where you're considering performance and area and cost. And here, this is an important thing. In fact, when I give you the exam discussing with main memory, accessing these slower main memory may have to be maybe up to 100 times slower than accessing registers or cache. So sometimes, just by designing this cache, it's going to cost you a little more, but you can really access it fast. The worst thing is, I need to perform an addition. Well, you're all very slow main memory, so I have to perform my addition, and I'm like, you're over here. And then you all fall asleep because it's a terribly boring lecture, right? Well, it's the same thing. If your computer took forever, you wouldn't want that. You just like, I don't need this thing. I can write, and computers wouldn't be the same thing. Or if you're using it in a space application like NASA, and you're using rote memory to go to the moon. Well, you need to have some sort of fast access, especially when you're trying to land on the moon or trying to perform communications with Houston. You need to be able to perform faster operations. So a lot of these memory technologies are being done specifically to figure out how we can trade off performance and cost and area. So here in 3.6, we're actually going to define cache and block. We formally define cache memory as the level of the memory hierarchy between the processor and main memory. And it's used to take advantage of both temporal and spatial locality. And so how that is actually done is there are blocks within levels of cache. So you have the processor, and so these are two different levels of cache, and I'll scroll down to show the whole diagram. What ends up happening is each block, which is the minimum amount of data transferred between cache and main memory, or a cache in the processor, or different levels of cache. It's the minimum value. So what do you think the minimum value in MIPS is? I'll give you a hint. Think about the registers. No, that's the amount of value that can be held in the bus. It's a good guess, though. But 32, you're on the right path. Actually, the answer is 32. The reason 32 values of 32, is because I want to swap in a whole new set of registers into the register. So every time you perform a swap, I ideally want to be swapping a block. So I have 31 block that's being operated upon in the data path. And then, so they're taking advantage of that spatial locality. We want all the registers that we're performing operations on to be very close to each other. And then when I'm done with that, I swap it out. I get yet another block, and that goes into my processor. I perform those operations. And then I swap it out, and so forth. And so that's why these ideas of temporal and spatial locality are important. The operating system, when performing the program, figures out where everything's going to be, which operations are going to be done, because you can actually, there's a whole process in compiling where you're actually figuring out how you're doing the specific piece and come out with a program tree, and you figure out where everything's being used, so you know the most efficient way of clumping them together. Here, so you know the minimum amount of data transferred. So the processor can hold 32 registers. So I want to swap those out, swap that back in. So this is the fast level. And then we're going to go into a lot more detail into how this is done in a moment with what's known as set associativity. So how do you actually associate between which blocks should be here and which, where the blocks are stored in the different levels? But let's say I have a program where I require 8 blocks. Well, typically I want those blocks to be right next to each other, taking advantage of that spatial locality. If an entire program can't fit in here, well, then I want the rest of the program to be here, right? The only time I need to access main memory during the execution of a program is if the program is so large that the entire cache memory can't hold it. So then what ends up happening is I swap out some blocks from level 3 from main memory, and then if I need this block to perform the operation, I perform a level 3 to level 2 swap, level 2 to level 1 swap, and then I get the code that I want into the registers in the data path. Yes, George.
So if the minimum, if the block size for MIPS is 32 bits, would that?
No, 32 register values. So it's 32, 32. So.
32 register.
Yes.
Okay, never mind.
It's a good question, though. Any other questions? All right, so you see how this works. So let's say this is main memory. So I discover that for some reason, the values that I need to execute my program aren't in the cache. So first it goes, so this was known as a cache miss, and we'll define all these in a moment. It goes here and it's a cache miss. Then it goes to main memory. And then I have to put that in there. Okay, well, I need to swap this in. So I swap that in. I swap another one out, replace it. And then I swap this in, take the values that were in the register, and put that in the old location. And so this is the fastest register. This is the level 1 cache, which is going to be the fastest cache. It's smaller but costs more. Level 2 is going to be a little slower. It's bigger, costs less. But the whole thing is we're trying to do that without avoiding this main memory that can take up 100 times faster. So does anybody have any other questions? Yes, first.
So in that diagram, the bottommost block, that's not main memory, that's level 2 cache?
No, it's level 2 cache.
Oh, okay.
Yeah, there's typically 3 levels. And when we get to if you don't mind holding off on those questions so we get to average memory access time, everything that you're kind of asking about will be clarified. I believe button. Any other questions? All right. All right, so here are the 4 main terms that you need to know in order to understand what's going on when we transfer these blocks and how to actually calculate the performance. So the first one is known as a cache hit. I am the data path. I am done with the registers I need, but I need another one. I didn't know some value. So I go to level 1. Is my register there? Yes. It's a cache hit. Swap it out. And we formally define it as that the requested data is in the cache. Read or write operation is performed directly in the cache without accessing main memory. So there's different levels. So if I have to go, if it's in level 3, I have a level 1 cache miss. I go to level 2, I have a level 2 cache miss. I go to level 3, I have a level 3 cache hit. Then I perform those swaps, and there's different time penalties for each one. But we still don't have to go to the main memory. So the hit rate is the probability that the requested memory item is in the cache. And as all probabilities are, the value is going to be between 0 and 1. So the reason we can calculate the probability is because of temporal and spatial locality. We know that by the way the operating system is grouping the variables together and where it's storing it and how it's storing it in the hierarchy, that there's a very good probability that we can access certain levels of cache. And what we're going to find when we get into these problems, and we get down to average memory access time here in a moment, is that the probability decreases with the levels of cache because of that spatial locality. We're trying to get everything as close to the processor as possible. So you go to level 1, it's a very high probability to be there. But if you miss it, there's a decent chance it'll be level 2. There's a less chance it'll be level 3 because they're bigger, but more than likely the stuff that you wanted to have there should have been closer to level 1. Do you see how those concepts of temporal and spatial locality tie into how we're actually doing this memory hierarchy? And so cache miss, so I kind of just alluded to. We formally define a cache miss is if the requested word, a word is 32 bits. So byte is 8 bits, half word is 16, and a word is 32. The requested word is not in cache. A block of words, which is the block of, which, to answer your question you had earlier, 32, that block of words is 32 words that we transfer in. Containing the requested word is brought to the cache, and then the processor request is completed. So it's brought into cache, it's brought into the registers, perform the operation, and it's done. And then the miss rate is the probability that a requested item is not in memory. And that's just simply 1 minus the hit rate. So the probability that it's there is 0.95. Then the miss rate is just going to be 1 minus 0.95, which is 0.05. Does anybody have any questions so far? Okay. I'm going to scroll past cache hit and hit rate, start getting into what this concept of average memory access time. Right. So, and this is the definition of average memory access time. But let me discuss what it is before we go into formal definitions. So the whole idea is that I'm going to access different levels of cache, and based on those probabilities and how much we know of what's in the on these programs or what's going to be run by a specific computer, and we know the performance and the actual probability that we're going to reach it in there, we can actually calculate how the average of all these accesses for each different level of cache in the main memory and put them together. So if I know it's a 95% chance it's going to be level 1, it only takes me 5 nanoseconds to access that level of cache. But then I go to level 2, that takes me 7 nanoseconds. where the percentage is 85% that I'm going to find it. The level 3, it takes me 12 nanoseconds to access it, but there's a 74% chance that if I look in level 3, it's going to be there. If it's not in everything else, if it's 73, then it's going to be 27%. It's going to be, let's go this way. So 95%, that means it's 5% chance that it's not going to be in. So it's 5%, but then we're at 80%, right? So it's 5%, 20%, and then we get to here, it's 20, 27 to 3%. So it's 5%, 20%, 27%. So the odds of which it gets a main memory are very low. We can actually, based on those probabilities and the access times from we know from our performance calculations, we can actually figure out that overall average. In this case, we define it formally as this known as AMAT, or average memory access time. So defining average memory access time, this should be 3.1, not 6.1. Given that TC is the cache access time, and TM is memory access time, and H is the hit ratio for the cache, so it's the hit rate. The average memory access time for a level 1 cache is the hit rate times the cache access time plus 1 minus the hit rate, which is the miss rate, times the access time of cache plus the access time for main memory. And the reason we do this is because you see me walking back and forth, but on the processor, I want to access the cache. I ask the cache, are you there? There's a certain amount of time it takes for me to ask the cache. If it's not there, then I have to go and take that certain amount of time and ask the memory. And that's why you have to add these together. And so this is example 3.1. This used to be section 6, but I moved it to section 3 before the data path design because explaining memory seems to help students understand the full data path design better. So this is example 3.1, not 6.1. Given a level 1 cache with a hit rate of 95%, a cache access time of 5 nanoseconds, and a memory access time of 100 nanoseconds, find the average memory access time. So we know our hit rate and we know our miss rate. So the hit rate is 95%. It's given in the problem. And we also know from the defined from the topical guide objective, the miss rate is 1 minus the probability, which is going to be 5%. And then we know cache access time and memory access time. So then what we do is we just kind of, even if you don't memorize the equation, you can think of it as you're walking through. So 95, if I have the processor and I talk to the cache and I say, are you there? And 95% of the chance it's going to be there, 95% of the time it's only going to take me 5 nanoseconds, right? So that means 0.95 times 5 nanoseconds. Now I should state that even though I do the calculations to show the difference here, that on an exam, that's sufficient. Write the equation, plug the numbers in. That's a sufficiently full credit answer. So 0.95 times 5 nanoseconds, and then I have to count for the next part, which is what happens when I have a miss. So here we calculate the miss rate, which is 1 minus 0.95. So that's 0.05 times cache access time plus the memory access time. So that becomes 100 plus 5. So that's why it's 105. And then when you do the math, it actually comes out to 10 nanoseconds. And so what I'm going to show you when we do a couple other examples where we add a level 2 and then we add a level 3, and what you see is actually the cache access time is going to come down. So it's 10 nanoseconds. You're going to see one that's like 7, and it comes out to 5.25. But what ends up happening is it looks like that. So once you add a level 4, it's slightly improved, but then money is going way up to do that. So typically what ends up happening is level 3 is where the design compromise comes in. I've done enough. I've really driven down my average memory access time. Anything adding another level won't give me much benefit, will cost a lot more. So to demonstrate that, example 3.2 is given a level cache with a hit rate of 95%. cache access time of 5%. This is example 6.2 is calculating performance increase. So in this case, level 1 cache with a hit rate of 95%, a cache rate access of 5 nanoseconds, and a memory access time of 100 nanoseconds, determine the speed up over the same processor without a cache. So in this case, AMAT no cache over AMAT cache. So if you remember, performance is execution time old over execution time new. So here we're having average memory access time, which is the unit of seconds. So with no cache, that becomes 0 because the probability of hitting a cache is 0 because it's just not there. Plus 1 minus a 0 of 100 nanoseconds. So it comes out to 100 nanoseconds. And here we calculated that's 10 nanoseconds, right? So it's going to be 100 over 10 nanoseconds, which means that our speed up is 10. So therefore, by adding a level 1 cache only, we have actually improved the memory access performance by a factor of 10. So that's why this memory hierarchy becomes very important. So I'm going to scroll up just a little bit beyond 3.1. And so TGO 3.7 is how do we calculate this when we're doing a level 2 cache? So 95% of the time, we're going to hit here 1, and we're at level 1 cache, right? And so if we do level 2 cache, yes?
I think the TGO is supposed to be 3.10.
Okay, so it's 3.10. I'll edit it to that's 3.11. So this is 3.10. Derive the equation for average memory access time for a level 2 cache. So AMAT, hit 1. I go to TC1. 95% of the time, I just go back to the processor, right? If I need to go to level 2, then it's 1 minus hit rate 1. And you see there's a bracket in here. So this is kind of where it becomes a little more complicated. There's a bracket. So then if I miss one, then I start going to, well, what happens if I go to level 2? So if we go to level 2, I have a hit rate of 2, plus I would have to access the first level of cache, then I'd have to access the second level of cache, and then take it back. But if I missed in the second level of cache, so it's 1 minus hit rate 2, then I'd have to go to level 1 cache, level 2 cache, level, and then main memory in this instance. And then, even though it's TGO 3.11 here, it's basically how do you derive the third level of cache. So basically, it's just this. You're going to start to see the pattern here. Hit rate TC1, then you have the miss rate, and then you have the block here. Hit rate TC2, the 2 access times. Then you have the miss rate for the second level of cache, and then hit 3. And I added a red bracket to make it more clear on the video here. So hit rate of 3. You're accessing the level 1 cache, the level 2 cache, and level 3 cache in this case. And then if you miss the third level of cache, you would, in this instance, you're missing 1, 2, and 3, and then need to access the main memory. So by deriving the equation in this way, you can actually calculate the average memory access time for a level 3 cache. So this is TGO 3.11. And so example 3 and example 4, 3.3 and 3.4, this shows how you can gain improved performance by adding levels of cache, but at the same time you're going to start to see decreasing returns. So example 3.3, the processor in example 3.1 is given a level 2 cache with a hit access time of 85%. So it's 95% for level 1 and 85% for level 2. And a cache access time of 7 nanoseconds. So level 1 was 5 nanoseconds. Level 2 is 7 nanoseconds. Find the average memory access time. So in this case, we have 2 levels of cache. So we use this equation from TGO 3.10. So hit rate times TC1 plus 1 minus hit rate. Then you hit rate at TC2, those 2 access times, and then 1 minus T2 hit rate, access time of cache 1, access time of cache 2, plus the memory access time. So here we know that it's 95% for hit 1, 5 nanoseconds for accessing that first level of cache. 1 minus 0.95 is the miss rate for level 1, so it's 0.05, times 0.85 because that's our hit rate for level 2. And that's going to take 12 nanoseconds because that's 7 plus 5. You see that? Why that's 12? And from here, what happens if I miss on level 2? 1 minus 0.85, that becomes 0.15 times 112 nanoseconds because that's 5 plus 7 plus 100. And on exam, that's sufficient, but I have written this out here because I want to calculate it out and show you that our initial one with just a level 1 had 10 nanoseconds. In this case, by adding a second level of cache, we have reduced the average memory access time to 6.1. And then in 3.4, we're doing the same thing, except we're adding a third level of cache now. And on the exam, you will get a type of cache access time problem with 3 levels. So the processor in example 3.3 is given a level 3 cache with a hit rate of 80% and a cache access time of 10 nanoseconds. So now we're finding the average memory access time. So in this case, we've written out this long equation, but now if we walk through it, we can feel intuitive of what's going on here. 95% times 5% for level 1, right? So if we miss, then everything else is blocked out. So here it's only 5% that we have to deal with any of these other probabilities. So it's 5% here. Here we get to the second hit rate, which is 0.85. And it's 12 nanoseconds because that's 7 plus 5 as we did in the last problem. If we miss, well then we go to 0.85. That's 0.15, right? So now we go to 0.8. So 0.8 is our level 3 cache hit rate. And that's plus 22 nanoseconds because we had 5 for level 1, 7 for level 2, that's 12, and then a cache access time of 10 nanoseconds at level 3. So 7 plus 5 plus 12 comes out to 22. And then this last part is our miss rate, so 0.8 plus 0.2, which is our, we have to go to main memory, times 122 nanoseconds, because that's 7. In that case, we have to go, this is a specific instance where we go from first level cache, which is 5, then we have to go to the second level, that takes us another 7 seconds, that's 12. We have to go to third level, that's another 10 seconds, so we're now up to 22. Then we have to go to main memory, which that's another 100 seconds. So in this case, it's 20%, of 15%, or 5% of the time we have to do this. And so the result there is that when you calculate that out, it goes down to 5.575 nanoseconds. On the exam, the question you do something like that, that's sufficient. I'm not testing you on your ability to put numbers into a calculator. So it's 3.11, TGOs 3.1 through 3.11. The example is 3.1 through 3.4. I'll post those online. Does anybody have any questions before I dismiss you? Did that answer generally your questions about cache?
Yeah,